All right, so continuing on with experiments, here's an example we're going to talk about. In 2007, deaths of a large number of pet dogs and cats were ultimately traced to contamination of some brands of pet food. I know you guys were fairly young for that, but that is a true story. If you want to look it up, I remember it quite well. There was food from like China that was not good or something. The manufacturer now claims that the food is safe, but before it can be released, it must be tested. In an experiment, so we're going to conduct an experiment to test whether the food is now safe for dogs to eat, what would be the treatments and what would be the response variable. So one thing that students kind of confuse here is that they think that the treatment is just going to be the new dog food. So we're just going to give the new dog food to animals and see if they get sick or not. But you always need to have groups to compare to. So you have to have some dogs get the new dog food and some dogs get some other dog food. Now we don't want to give them the old dog food. We know the old dog food is sick, so it will make them sick. So that would be cruel and unusual, and we're not going to do that. So what we're going to do is we're going to have the treatments be the new dog food and some other food known to be safe. Some other dog food known to be safe. And there's a couple of different reasons you need to do that, is because if the new dog food, you give it to some dogs and one or two of them get sick, do you know for sure that they got sick because of the dog food, or do you know maybe they just got sick because dogs get sick? Especially if you give them new food. Some dogs, just by the fact of getting a new food, get sick. That could happen in this group as well. These dogs could eat this food that we know the food is safe, but they might just happen to get sick by chance, and it not be because of the food. So since both groups have that ability to just happen to get a dog here or there get sick, you need to make sure both groups get the different food. That way, if some dogs get sick in both groups and it's at the same level or rate, then you can kind of feel that maybe that's by chance and not because of the food. But if this group gets a lot more sick, the proportion of dogs getting sick is higher than in this group, then we can kind of isolate and say, oh, well, we think it's because of the food. So you got to make sure you always have something to compare. The response variable would be the health of the dogs, or did the dogs get sick, which is a categorical variable. So after running this experiment, I would probably create some sort of a percentage or proportion to summarize my result, the percent of the dogs that got sick. Just so you know, confused with the word factor and treatments, the factor would be dog food. That's what we are manipulating and controlling. The treatments are putting together different levels of dog food. So in this particular example, the different levels of food would be the new one and the other food known to be safe. We could also go down into amounts. Maybe some dogs get a lot, some dogs get a little. Those would all be different levels of treatments. All right, there are 4 main principles of experimental design: control, randomize, replicate, and block. The first 3 are required. Blocking is not required, but should be done in specific examples. So you want to make sure you control sources of variation other than the factors we are testing by making conditions as similar as possible for all groups. So you want to make sure that both of these groups are getting the same amount of food, same amount of water, same amount of exercise, same amount of care, same amount of whatever it is, treats, you name it. Because if you don't, then you don't know if one group got more sick because of these other factors, because of the other factors, or because of the dog food. So you want to make sure you control all possible sources of variation that could exist. You must have randomization. Randomization allows us to equalize the effects of unknown and uncontrollable sources of variation. For example, what if some dogs are just prone to get sick? Well, you don't want all of those dogs in one group, so that's why we use randomization. That act of randomization should put the dogs that tend to get sick in both groups. So once again, we are controlling that aspect, that other sources of variation. It does not eliminate the effects of these sources, but it spreads them across treatment levels so we can see past them. So if you have a few dogs who just get sick naturally in both groups potentially, that equalizes that result. And then we can look to see if this group gets more sick than that group because of the food. Without randomization, you do not have a valid experiment. And you will not be able to use powerful methods of statistics to draw conclusions from your study. So it's really important. Replicate. You must replicate the experiment, applying the treatments to a number of subjects. Later in this course, we'll learn how our sample size or group size helps us calculate how precisely our statistics, that's what we get from our samples or from our experiment, estimates our true parameter. And that's applying that knowledge from this subgroup to everybody. We can only really do this if we have replication, if we have a good number of people in our groups. You don't want to just have one dog in one group and one dog in another group. You want a good number of dogs. What is a good number? Just depends on the scenario. We'll talk more about that later. We're also going to learn later on how to calculate a margin of error. This has been mentioned once or twice in class, but this is just that expectation of variation. And it's just a measurement of how much variation we expect and then what kind of would be too much or unusual variation.